Okay, everyone, welcome back. This next section, I'm going to talk about one specific application, which is time series clustering. Okay, time series clustering is a sort of a specialized branch of clustering analysis because of the tricky nature of time series and finding distance metrics on time series. I'm not going to actually talk about that in any great detail, but I'll just make you aware of the fact that there are some fairly sophisticated and useful methods for extracting features from time series that allow you to group them sensibly for your particular applications. So if you're interested in some sort of correlations between really high frequency data, there are ways of doing that. If you've got high frequency data but you're much more interested in the low frequency correlations, there are ways of doing that. They involve things like finding different frequency responses or splitting out the different frequency signals within the data, or aggregating the data over different sort of time lengths. So if you've got 5-minute data, you might add it up over 5 minutes, 15 minutes, hours, 3-hour blocks, 6-hour blocks, 12-hour blocks, and look at the correlations and all those different derived features rather than the raw series itself. So there are a range of different things which you can do to build your features out of time series, and you can be even really quite creative with what you do there. In some of the work we've done in the past with one of my past PhD students, Chanaka Kirthasinger, we actually turned the feature selection problem itself into an optimization problem and determined features out of time series using a genetic algorithm. Okay, so you can get as creative as you like. As in my introduction I talked about principled AI, I don't like things like particle swarm optimization and genetic algorithms. They are, in my opinion, fairly crude heuristics, but sometimes when you really have no idea of the structure of the problem that you're faced with, you have to rely on heuristics that have a proven track record. So that was a setting where something like a PSO or genetic algorithm was very appropriate to use. So, moving on from that, the type of time series clustering that I'm going to be talking about today is actually clustering using what we call side information. So that's information that isn't contained in the series itself, it's other information that you may hold about the customers. Okay? The particular framework we will use is called a Bayesian hierarchical model, or a hierarchical Dirichlet model. We will have a look at what a Dirichlet distribution looks like. Well, it's a bit exotic, it might not be one you're familiar with, but Dirichlet distributions are excellent at mixing over a finite set of categorical variables. That's what they're used for in a Bayesian hierarchy. And we'll see how we do that in this particular context to give you an idea of how you might use something like Bayesian statistics for this sort of clustering task. Before we start, though, I will talk just a little bit about what Bayesian statistics are particularly good for. We haven't seen them yet. In the material I covered earlier, we didn't see anything Bayesian. It was all frequentist approaches or non-parametric approaches. But the idea behind Bayesian methodology is that sometimes looking at the data and knowing what you know about the frame of the data that you've collected tells you that you don't really know about the whole world. Okay, so in the voltage data that we looked at before, we had 45 customers. What if that came from a medium voltage feeder with 3,000 customers connected? What does our sample of 45 tell us about the 3,000? What if it was 45 spread out over 100, well, it won't be 100, over 45 feeders, each with 3,000 customers associated with them? What can we do then, right? We can't really generalize that data with any confidence, but we still want to try and derive some insights. So when you have small samples relative to the population, it makes sense to incorporate in a systematic way some sort of measure of uncertainty or a way to handle that uncertainty, and the Bayesian framework allows you to do that. So the paper, this work is based on a paper that we had published, or it's not quite published yet, but been accepted into Smart Grids, IEEE Smart Grids. The first author's name is Tom Power. It's very good. And the data that we're going to be looking at is from the Ausgrid Smart Grid Smart City dataset, which I'm sure some of you have come across, which has been really useful for us as academics to mine and find various things out of that. Even if it's not particularly useful in an industrial sense, it's useful for us to come up with methods based on that data. So if any other network companies want to ever make data like that available to academics, I encourage you to go all the way and release it for us. So the title of the paper here involves the phrase, "For synthesizing residential solar generation and demand data." Okay? So our goal here is to use existing information about known customers to generalize across all customers so that we can improve the sort of simulation studies that we're doing. Okay, so if we have a subset of the customers sampled, we have a lot of information about them, and we know there are other customers out there, obviously, and we don't have their data, but we know some of their other characteristics. We know that they're a working age couple living in a house that has gas appliances. Can we use that information to generalize what we expect, or give an idea of what we expect their energy usage to look like, so that we can fill in the missing gaps in our simulation studies? That was our goal with this particular piece of work. The way we started on this was another method that I think Anna mentioned on Tuesday, which is maximum a posteriori Dirichlet process mixtures, which is just a very fancy way of allocating labels to customers, right? So clustering customers, right? So we had information on things like for their different. So that each time series was a day. So we had day types, number of residents. We had a bunch of other things as well. We had, like I said, gas appliances, details about some of the other appliances that were in the house. So how many fridges they had, whether or not they had air conditioning. Okay, a few of these other important high energy demand features of different customers. We clustered based on those features. For PV, we had the features were things like the PV capacity, the panel orientation and tilt. Okay, so fairly a smaller set of features there, but nonetheless we could cluster PV installations based on this sort of data. Okay. And then the time series model that we identified based on these clusters, it was not particularly sophisticated. I'm happy to say that. It's something we're continuing to work on, but it doesn't really matter for what I'm showing you here, for the clustering and synthesizing problem. The underlying time series model is kind of a separate independent module. So we used a conditional Markov chain model, which is something that works. It does pretty well. You'll see at the end it does pretty well. Okay, gives statistically similar looking traces. It's not the bleeding edge of time series modelling for these sorts of traces. There are much more sophisticated things we could have done, but it's independent from what we're doing here with the clustering based on the side data. Okay, so we clustered. We got all the houses that had an air conditioner, 2 fridges, 5 people living in them. That was one group. You know, we had these different groups that we could sort of identify what they look like based on their medioids or exemplars or whatever they were. We did this clustering. That form of clustering actually didn't really matter either. We had these clusters. We had these clusters with certain numbers of customers in them. And what we could have done, if we're applying what's called a frequentist approach, is we could have just taken the frequency with which customers appeared in the different clusters and called those the probabilities of the other customers, the unobserved customers, occurring out in the wild. But we knew we had a small number of customers relative to the size of the system we were trying to simulate. So this is a problem that statisticians have grappled with for quite a while, and the way to approach it, as I highlighted earlier, is to use a Bayesian methodology. because it allows us to moderate our uncertainty in the estimates given by the counts of clusters using a principled method that takes into account the size of the sample and the confidence with which you hold those estimates, the frequencies. Okay? And the method, the specific method, is this Dirichlet mixture model. Right, so we're going to do a little bit of probability theory because it's one of my favourite topics, believe it or not. First of all, multinomial distributions. Who knows what a Bernoulli trial is? Remember that one? Bernoulli trials are coin toss, binary outcomes. Okay. So then if you do several coin tosses, say a set of coin tosses with 5 trials, we have what's called a binomial distribution, which gives you the probability of certain numbers of successes, heads, whatever you want to call them, occurring, right? Given the underlying probability of a success occurring in the Bernoulli trial. Okay, so that's Bernoulli to binomial. A categorical probability distribution, or a categorical process, is one where rather than a head, you're rolling something like a die, right, which has 6 sides. It has more than 2 outcomes. Okay, so any single trial that has more than 2 outcomes is a categorical variable, and there is a vector of probabilities associated with each outcome. So for a die, you have 6 sides. Hopefully, if it's a fair die, each side has a probability of occurring of 1 on 6, but you might have a biased die that has different probabilities in general. That's a categorical variable. The equivalent probability distribution to a binomial distribution for a categorical variable is called a multinomial distribution. Okay, I've got 2 different forms of the multinomial distribution up there. One which is sort of the direct form, and this one here, and the other which involves the use of this creature called a gamma function. Okay. The gamma function gives us an analytically tractable way of enumerating these horrible factorials. Right? Because once n gets big, they're computationally difficult to calculate. Just to explain the notation a little bit more, what we have here is the probability for a random variable x, the probability that it is equal to a particular value x, so that's the probability that in, say, 10 rolls of a dice you get 3 threes. Okay. Given there are 10 rolls of the dice and the probabilities of any one of those sides coming up is equal to this thing here, where we take the sum of all the probabilities, sorry, the product of all the probabilities raised to their, each of them raised to their outcome, okay, the count of their outcomes. So if it's 0, that's 1. If it's 0, that's 1, it doesn't affect the value. And if it's not 0, it does affect the value. Multiplied by the different ways that it could arise, the orders that they could arise, and then summed over the ways that everything else could happen. Right, so it's a bit ugly, but effectively it just gives you the probability of different outcomes arising. Okay, so I didn't quite get that right. X is supposed to be the probability of a particular outcome. So in 10 trials, it might be 3 threes, 2 twos, adding up to 10 outcomes, right, with them all specified. That's what that vector x there is, a specific outcome. Okay, so this probability distribution is the one we could sort of use for when we're trying to allocate our class labels to unobserved customers in the problem we're dealing with. Okay, we have the P's, they're the probabilities given by the frequency of different clusters arising in our data. And for another 50 customers that we're adding to our system, we could just draw them according to the multinomial distribution and get a pattern of what they look like. Okay, the problem is we have uncertainty around that vector of probabilities P. We're really not sure what P is. We've only got one sample. We've got some counts. We're still not sure what's going on there. Okay. So how do we handle the uncertainty in the P? So that is this P here, which is one of the key parameters of the distribution. Okay. And this is where the Dirichlet distribution comes in. Okay. So a Dirichlet distribution, as I say there, of order k, that's the size of the sample, is used in the context of a random experiment that has more than 2 outcomes. Okay. In Bayesian inference, we say that the Dirichlet distribution is a conjugate prior of the categorical and multinomial distributions. Now, Anna talked about conjugate priors, but she didn't use the words. She was talking about updating Gaussians with conditional probabilities given by Gaussians. Gaussian distributions are self-conjugate. If you update a Gaussian probability distribution in a Bayesian sense, using Bayes' rule, where your prior is Gaussian and your data generation process, which is generating your evidence, is also Gaussian, the resulting distribution is a Gaussian. There are huge computational benefits for doing that because you can just work with the means and variances, and Anna highlighted that in the case of Gaussian processes. Here we don't have Gaussian distributions because we're dealing with categorical data, not continuous data. Okay, so we have to use a different set of tools. Conveniently, probability theorists have come up with this particular way of setting up conjugate priors for multinomials, and that's using Dirichlet distributions. Okay, so if your prior is given by a Dirichlet distribution and your data generating process is given by a categorical or multinomial distribution, then your posterior distribution is again given by a Dirichlet distribution. Okay, so what does that mean in a real sense? If the probability distribution that you have is a Dirichlet and you roll a dice because you're trying to work out what the weights are on your die, right? That's a multinomial data generation process. If you update, given the conditional probability of observing something on the outcome of the dice, given what you know about your current state of evidence of the biases on the dice, you update your Dirichlet prior with that information, the right distributional assumptions about it, you get another Dirichlet posterior. Okay. How do we do this? It's actually really simple. The Dirichlet distribution has these parameters, alpha. You can think of them as the weights or the concentration parameters associated with each of the possible outcomes. Okay, so the category labels on your clusters. The alphas aren't frequencies; they are counts. They are just the straight count data. Okay. So if you have 50 customers and 5 classes and 10 in each class, then your vector of alphas is 5 tens. Okay, and that makes updating this distribution in the light of more evidence really simple, because you observe the next customer, allocate it to a class, add 1 to whatever class that was, and that's your Bayesian update. So Bayes' rule, which in general is a horrible thing to try and compute numerically, has an awesome tractable analytic formulation here. And this is why Dirichlet distributions are one of my favourites. And the fact that we can use, so now hopefully you've seen 2 tools over the course of the week for embedding probability processes in a Bayesian hierarchy. One where we have a Gaussian process, so Gaussian data generation process updating a Gaussian posteriors and priors. And this now, for categorical data, the multinomial or categorical variables being used to update a Dirichlet prior. Okay, armed with those 2 tools, you can do an awful lot in Bayesian statistics. So get to it. Let's have a bit of a deeper understanding of what this Dirichlet distribution looks like. Sorry, I had to rotate this picture to make it fit on the slide. 3 different Dirichlet distributions there. The first distribution has a low number of counts and equal counts. So the alphas might be all 1s or 2 or something like that. And what that means is that the evidence for a particular data generating process being the true process in this 3 outcome space. So you know what this is? This is a simplex. Okay, so a simplex in 3 dimensions. There are 3 possible outcomes for this for this particular categorical variable, and the simplex is the hyperplane that satisfies the constraint that the probabilities add to 1. Right, so if you think of it in three-dimensional space, it's like a triangle on 3 dimensions where each of the vertices are at 1 in the particular dimensions, where everything else is equal to 0. And then you've got a triangle that links those things. Simplexes like this, the Dirichlet distribution is always embedded on a simplex. In higher dimensions, it's always a hyperplane. A simplex is a hyperplane, so 1 dimension less than the actual data process that you're looking at. It's the hyperplane where all the probabilities add to 1. In this case, we have, I'm taking a guess, because I can't remember exactly how I generated it, that we have 2 observations for each possible outcome from our data generating process. The imaginary 3-faced die has been rolled, and we've magically got the 3 outcomes twice each, which means that, first of all, this is symmetric. Okay, we don't have any evidence for a bias in the 3-faced die. And secondly, we're not very confident in that. So the concentration of the probability at around the midpoint isn't very high. Okay, it's fairly uniform. So these 2 characteristics of the Dirichlet distribution come out from the number of counts, both the concentration on a particular outcome, but also the confidence with which you hold that estimate of the outcome, okay, of the data generating process. In the second plot here, we've had more positive outcomes for more positive counts for this particular outcome, indicating to us that the distribution over all possible data generating processes for our 3-faced die is biased towards this outcome. Okay, so face number 2 has a higher probability. The probability distribution over the probabilities of outcomes of the dice is concentrated towards outcome 2. Now, in the third case, who wants to take a guess what's happened in the third?
They're equally likely, but you have high confidence in that?
That's right. They're equally likely, but we have high confidence in that. Yeah. Right, so we've seen a lot of samples, and they've told us a lot about the process, and this is telling us that we're confident that it's an unbiased 3-faced die. Okay. So how do we use this hierarchy of probability distributions in our clustering problem? So as I said earlier, after doing the clustering, we have this vector of counts. We call them alpha. We interpret the alphas as the concentration parameters of a Dirichlet distribution. We call them hyperparameters because they aren't the things we're directly interested in, but they're what we're using to moderate our uncertainty over the parameters we're particularly interested in. So these are concentration hyperparameters. That's the numbers, not the frequency of the observed customers in each cluster. Then in order to sample a particular new customer and get their class that they're associated with, the first thing we do is we sample a probability parameter for a categorical variable from the Dirichlet distribution. So we go to one of these things. Let's say we're going to the middle one, and we sample P from this space, okay? Or we sample a vector of P's from this space. So given that the probability is concentrated around here, the chance that we end up with a P that has a higher value closer to 1 for outcome 2, or cluster number 2, is greatest. But sometimes that just doesn't happen either. Okay, there is a chance, a positive probability that we just happen to end up out here. But more likely than not, we expect to be around there. This gives us the distribution. This gives us the parameter for the distribution over the features, which itself is given by a categorical variable, right? And then we actually apply or assign the class label to the unobserved customer by sampling from the categorical distribution itself. Okay, so the terminology that's used is that the Dirichlet distribution moderates the parameters of the the categorical distribution, right? And in that way, it allows us to formally handle the uncertainty we have in the estimates P, okay? If we use a frequentist approach, we would just take P as a given from the frequency of customers arising in the different clusters. Okay, but that doesn't allow us to express anything about the confidence we have in that estimate P itself. That's the hard part. If you read papers on these types of models, you will, without any doubts, end up seeing something that looks like this, okay, which is supposed to summarize the structure of the model in question. Okay, where A is the vector of counts. Q, this should be A. Up here I've used P and here I've used Q, sorry. Q is the parameters of the categorical variable given the alphas, which are distributed according to the Dirichlet distribution, and then the labels themselves are given the Q are drawn from the categorical variable. Okay, this is actually a really simple hierarchical model. If you ever have a look at any of the astrophysics data, where they're trying to do some very, very funky estimation problems involving things that they can't really see, and a whole bunch of priors based on physics, you'll see a column of these sorts of things that might be sort of 8 different elements long, where they have various physics-informed priors feeding into sparse observations and then eventually getting down to some prediction. It's impressive, really, how well the mechanics of this stuff works. And a lot of the research that goes into making this work has to do with the cases where you don't have the nice analytic relationship between conjugate priors and the data generation processes. You have to use numerical techniques, and numerical Bayes updates boil down to big problems in numerical integration, basically, and they can be very time intensive. But when you're doing astrophysics, you seem to be able to get the resources you need to do this sort of stuff. If you can use the analytically tractable cases, then you get a lot further. Right? We don't have any failed astrophysicists in the room, do we? That are excellent. Okay. Right, I've gone through that a little quicker than I thought I would. So how did it work? So without knowing, well, I gave you the brief insight into the underlying probability, the underlying time series models that we used. So those class labels were then associated in our paper with a time series model. Okay, so the class then gave you a time series model. The time series model itself was estimated on the observed data. So the customers were classed. They were clustered. The customers were clustered. And we then identified certain conditional Markov chains as our forecasters for the actual generative processes for the series that we were interested in. That itself was another involved process that isn't really to do with clustering, so I've left it out. But those models themselves, we could have used whatever we wanted really for the time series. Those models themselves were then sampled to generate synthetic data that hopefully, and we did have our fingers crossed, hopefully looks like the real world data. These are some plots sort of giving you an idea of how similar we got things to look without investigating the actual time series models in too much detail. These are synthetic weekday demand profiles over a day. What we were really looking for is various organisations will provide you with average load curves for the day that are kind of useful and kind of not, because everyone's really interested in the variability in load when you're trying to size networks and that sort of thing. So what we were trying to do was come up with this generative process that gave us the variability we needed. So then we could look at those extreme cases, looking for things like ways of generating probabilities of exceedance values and things like that. Okay, so this sort of variability in the synthetic data that we could generate using the clustering and then the time series modelling was actually really very useful for that purpose, or at least we think it was. And here's an example of an equivalent sized set of customers, the aggregate load over a week compared to the data that we trained it on. Okay, there's a couple of things I want to point out there just so you know where it went wrong. First of all, the peaks aren't as high, right? And that's a problem because that's really what we were trying to get to. Even if the shapes are quite similar, the peaks aren't as high. So this here boiled down to the blue line when you add it all up. And we have some fairly good understanding of what drove that, which I can talk about if you want to hear about it, but you've got a question or a comment?
Yeah, just a question about the number of clusters that you come up with to generate this synthetic data.
Yeah. So in this case, I think we came up with 9 clusters. Having said that, one cluster dominated. It had a huge proportion of the customers in it. Something like 85% of them were in one particular class. Now, part of the reason for that is we didn't actually include any statistics from the time series themselves in our clustering. We're seeing how far we could get without that. If we would use the statistics from the time series themselves or some sort of features from them, I think we would separate out that very large cluster. That's something that Tom Power is working on at the moment. One of the reasons we didn't go down that particular path is once you start looking at the time series, there are third or like additional side information that we need to get to explain the variability in the load. That would do a good job of explaining the variability in the load, the biggest one being the weather. And we didn't have the weather data in hand when he started this work. And that's what I was going to get onto, so thanks for asking that question. The main reason we think, anyway, that the peaks aren't as high as we'd like to see, they don't match the peaks of the actual original trace here, is that we haven't taken into account those external forces that are driving electricity load, like calendar events and particularly the weather. Okay, that's what we're working on at the moment, to try and feed that all into the model as well. Right, but bit by bit we'll get there.
Consider the geographical location?
The geographical location, so by postcode, there was some sort of partition, maybe it was local government areas that was applied, but I don't think it was informative for this particular data set, and that has to do with where the Smart Grid, Smart City trial was run. It's a fairly uniform population. I'm thinking someone from Ausgrid, if there's anyone here, would probably tell us more about it. But it was up in the Hunter Valley, and there wasn't great variation in the geographic location to start with, so that didn't turn out to be particularly informative. So it wasn't included as a feature in the final product.
The geographical location of the Smart Grid, Smart City, and there are 2 climate zones involved in the data set.
Yeah.
A cold and mild. So.
Yeah, for sure. And we did include that feature in the initial clustering analysis, but as I said, it didn't turn out to be particularly informative. So I'm fairly confident it was dropped out. I mean, I could double check that, but yeah. They're exactly the pieces of information that you should include at the outset, though. So I was talking in the break about sometimes the best way to start with these sorts of clustering problems where you do have a lot of side information is to throw it all in and then pare out the bits that aren't useful to you to improve the insights into the things that are informative. And that's kind of the art of statistics, right? Model selection is a big branch of classical statistical theory. Yeah. Okay, so we will get into classification now. Okay, so that was all I was going to say on clustering. So classification is a branch of supervised learning. So supervised learning, we were doing clustering before, that was unsupervised learning. So now big picture stuff, we're switching focus to supervised learning and in particular classification. Supervised learning is a branch of inferential statistics and machine learning where we have training data. We have the inputs and the outputs. Okay, the 2 big branches of supervised learning are regression and classification. You've all done a stats course at some stage where you were exposed to the least squares estimator for linear regression, I'm sure. You have your x's and your y's and you find the line of best fit according to the quadratic loss, right? So this is familiar to you, that's good. Classification, the key difference is that you don't have a continuous or numerical even variable as your output. You only have, in the general case, categorical labels as your output. So you can't draw a line between things that are either one or another, or a third thing which doesn't even have an ordinal relationship to what you're trying to classify. Okay, so although they're both supervised learning problems, that's regression and classification, you just can't handle them using the same tools to a point. But the key thing that links the two of them is that we're trying to infer some sort of function that maps from the inputs to the outputs. Okay, we're going to here concentrate on linear models for doing this, because linear models are tractable, they're easy to implement, they work most of the time, and they also form the foundation of much more complex classifiers like neural networks. So in this coming section, we're actually going to do a deep dive into one neuron in a neural network to have a look at what goes on in just that one neuron. Okay, and it'll be a logistic or a sigmoid function giving us logistic classification. Okay, we're going to hopefully go fairly deep into that and get a deep understanding of what's going on there, why it works, what its limitations are, why it's easy to train versus some things which are not easy to train, and why when you have really, really large data sets, you can forget your neural network and just go back to something more simple like that. So classification is, the task in classification is to find this good mapping of input data to class labels. Okay, the way we measure good is a very important part of this. So just like with clustering, the distance or similarity metric is important. For classification, the loss function or error function can have quite a profound effect on how your classifier can be trained, how well it performs, and various other things. And there's a bit of flexibility in how you choose a loss function. We'll focus on one in particular, but there are a range of different loss functions that you might be interested in, particularly when dealing with classification problems where the risks of, say, false negatives are particularly high. You might want to find some slightly more exotic loss function that takes that into account using weights or different functional forms. Okay, so although we frame supervised learning as being the problem of minimizing a loss function, that's not really the goal. That's just a proxy for what the real goal is, which is to come up with a system that can work out how to categorize inputs based on outputs and generalize what it learnt from what it's seen before. Okay, so this loss function is only a tool to get us there. So there's no hard, like I'm saying, there's no hard and fast way of setting the loss function when the goal is really generalization. How do you learn from what you've seen about unobserved cases? Now, in what we're going to look at here, we're going to assume a lot of things about the system are pretty similar. Okay, so the system under question is not changing dramatically, and you're just trying to find that nice mapping. There are a harder set of problems which are tackled by what's called transfer learning. The whole context of the learning and the future classification problem are quite different. You're trying to learn in one setting and then learn things about it in an unseen setting that's quite radically different. Humans are remarkably good at this. Machines, not so much. So humans can do classification tasks on new problems that they haven't seen really quickly. Just training off, we call it training, but from our experience of just a handful of new examples. Right, we get it. And no one understands yet why we can do that so well. The neural architectures people still can't work out what's going on in the brain compared to what goes on very effectively for a lot of classification problems using neural networks. Okay. So neural networks use things like backpropagation and gradient descent and stuff that mathematicians really like. Your brain doesn't do backpropagation. Okay. There's spikes and discrete changes, and we can't work out the biology of it, so we can't quite work out how to emulate it in a mathematical formulation yet. Okay, it's the neural computation people are really, really eager to unlock this particular puzzle because they are adamant that it will give us not just an insight into how our minds work, but also much better classification tools. Okay, so keep your eyes posted on that sort of, eyes open for that sort of development. If something big happens, it'll be, it could be quite revolutionary, but we're not there yet, so that's just for the future. I got a little bit off topic there, sorry. The simplest way to sort of learn this generalization, to get an indication of the generalization error or the how well your classifier learns, is to do something like have a holdout sample. Right? So train the classifier on one set of data, have a holdout sample that you then evaluate it on. You're probably all familiar with this methodology. It can be raised to the nth degree by repeatedly partitioning the sample and looking at how well your classifier works on average over different partitions. So things like k-folds verification will allow you to get there. I'm not really going to talk about that sort of stuff in any great detail, but there are methods for automating these sorts of evaluations of classifiers available in all the major machine learning packages, and that's something for you to do for yourselves when the time comes. Just a quick note that the statistics literature and the machine learning literature often use different terminology, which can get quite confusing. I switch between the two of them, which is probably just as confusing for you guys. So observations are often called instances, independent variables or inputs are called features, and categories are called classes or outputs. There's several different ways you can express the same thing. I will have mixed terminology on these slides. I will be inconsistent in what I'm saying out of my mouth as I'm talking up here. If it's not clear, just ask me to clarify what I'm talking about. Okay, classification methods. We're going to go through the same sort of structure as we did in the earlier session. So there are a lot of classification methods, just like there are a lot of clustering methods. Some of them are heuristics. A lot of them are very similar to the clustering methods that we've already had a look at. And some are so complicated that even the people who research them don't really, in my opinion, know what's going on. It's actually, for artificial neural networks, at the cutting edge of what's going on with artificial neural networks, we're seeing fantastic performance in classification and control problems using neural networks, and a lack of transparency around how particular novel architectures are being trained, what instances they're being trained on, why they perform well, and why people can't replicate results when they don't have access to all that sort of information. Okay, so it's a methodology of science issue that's arising in this area, being driven by the fact that the things are actually really useful when you train them properly. But let's have a look at here's a classification problem. Okay, we have two input variables, yeah, or features. We have 5 classes given by the colours. What's some really simple ways we could classify these, train a classifier, or come up with a classifier for predicting a new data point, predicting the class membership of a new data point. Okay, let's say it's there. It's not meant to be moving. Yeah, it's nearest neighbour. Okay, so in that case, what's our classifier and what's the training problem?
It's not training, it's just measuring the distance.
Yeah, the training is just loading the data.